So good morning. Thank you very much for being here. I am very happy to be here in Germany, in this very nice laboratory, to be in Germany with all my friends. So let's start. I have the first presentation. So we will try to speak about EMI debugging, EMI considerations in some kind of introduction, no? And during the 2 days, we will have more opportunity to go in deep in technical subjects and including some demos, no? So we will have some demos with real instruments. Now in the first part, we will be talking about challenge and early review of your design, something that is in any book about EMI and EMC. And the first thing to do, obviously, is to acknowledge, to say thank you to MPS and Rod and Schwartz for inviting me to be in this nice laboratory, this EMC laboratory, something that I would like to have close to my building in Spain. No? So I hope you will enjoy the visit today. Let's start with the problem. No? Remember, we are interested in EMC, so you must be interested in two different ways. You need to consider emissions, you need to consider immunity. Many companies are especially worried about emissions. Don't forget immunity. If you have a very important problem in immunity, usually the solution is more difficult than solving emissions problems. And remember, in radiated or conducted emissions and immunity, you need to identify who is the culprit and who is the victim, okay? This is the general view. Then you go to the laboratory. And in the laboratory, you have a lot of tests to do. I have explained here only two of them. It's the idea of radiated emissions and the idea of conducted emissions. You need a special instruments, special antennas, special devices like the line impedance stabilization network, and then you will put your device in some specific setup, trying to measure how much is the energy that is going far from the DUT, or you need to measure how much is the noise you are injecting in the mains network, in the power supply network, DC, AC, or something like that, no? And then you obtain the results, something like this. All of you know about this. Sometimes you are failing on this, like this. You are failing at specific frequencies. You go with the market to the peaks, and you find that these peaks are related with the frequency in your design. The clock frequency, the driver of your IGBTs, or some specific oscillator you have in your circuit. Sometimes when you are comparing the limits, the peaks with the limits, the result is something like this. So instead of some specific frequency, you have a mountain, or you have a frequency that is not related with frequencies in your circuit. This is typically due to resonances or parasitic oscillations. This is one of the most difficult parts to solve any EMI problem, to identify where this energy is located. Okay, so now we are failing. When it's important to consider EMI to have success? At the beginning of the project. Remember, if you are at the beginning of the project, we are here, and you find the problem in EMI, the solutions are a lot. And the cost for that solutions in production is very small. It's the idea of how you do the stack-up distribution, or where you put the DC-DC converter, or if you put the traces at this distance or this distance, or you introduce a small ceramic capacitor. This is usually cheap per unit of production. Obviously, you need engineering. But what happens if you have the problem in this stage? There is a lot of cost per unit of production, and you cannot change things in your product. For example, the PCB cannot be redesigned. The mechanical design is finished. The cables have been selected. It's impossible to introduce a seal. Or we can introduce this filter, but the filter is, I don't know, €3 per unit of production. And this is a terrible problem. Okay, so when you are failing in that situation, you obtain a lot of different problems. One, delays to go for the market. In my experience, if the problem is not very difficult, you will spend weeks, typically, to prepare the changes that goes to production. But if the problem is medium or difficult in EMI, you will spend perhaps months until you obtain a new prototype that is able to pass the test. Second, unexpected cost. thousands of euros, thousands of dollars. This is because you need to redesign, you need to prepare new prototypes, you need to retest, and perhaps you need to hire consultants to solve the problem. Third, you need additional tests. We need to retest. And this is important because this retest means time and money, cost. Another important thing, image degradation. Your customer is waiting for the product and you need to have some delay. So this is something like you can lose confidence of your customer in your capabilities. Size and weight. The solution is to introduce this filter, but it's very big. We don't have place for the filter, or it's heavy for the weight we want for the product. Another important result, failures in the field, especially if you have not designed the circuit for immunity. So you will have units of the product coming to the company from the customer because they are failing in ESD or transients in power supply or something like that in the field. And finally, stress. When the people is in this situation, in the area of production, people is very nervous, okay? Who has the responsibility? The EMC guy, okay? So remember, every time we do a redesign, we will need to retest. So it's not so easy to change things when you are in the process of finishing a product. Why we fail? Let me think some ideas. Obviously, this is not a complete list. We fail because first, we don't have time. We say, we will do the EMC later. Second, we assume that the product will fail in the first, will pass in the first trial. Look at this. This is from Intertech. This is a very important EMC laboratory in the world. You can see that in the first trial, 50% of the companies fail. Perhaps in medical equipment, it's 40%, because medical equipment are typically designed more in detail. You need to go to the second trial to go to 6%. And then in the third trial, you will have a 1%, 2% of companies failing. So you will not pass in the first trial. Third, perhaps you are failing because you are applying incorrect EMC regulations. You need to know what kind of test you will need to apply to your product, not to discover what test you need to pass at the end. Fourth, perhaps you are using a non-compliant product or component. For example, a power supply. Oh, we have found a very cheap power supply. Very cheap usually is not equal to quality, in my experience, okay? Many people say, I am buying very cheap components. Wait a moment, I want the same price. You don't compare the quality of the component, it's not cheaper. It's different, it's another component. Idea, no EMC knowledge. This is the other or an important reason to fail EMC test. People in many companies don't know about high frequency design. They are not familiar with hidden schematic, parasitics. That is because many people talk about EMI like magic, because many of these effects are not in the schematic of your product, of your circuit, okay? And that is because my laboratory is called the HF Magic Lab. HF is high frequency. Magic comes from this idea. Another important idea, late response. I am sure that you know about these ideas. For example, we start the EMC analysis when the customer knows that the product is close to be finished. This is a very big mistake. You need to solve problems and the customer is waiting for the product. Second, pass the final product to the EMC engineer, he will solve the problem. In the meantime, while the EMC designer or the EMC guy is solving the problem, you do changes in the mechanical design, in the cables. And additionally, you don't say him that you are doing the changes. Another important thing, if the product fails, you can put the EMC engineer working in the weekends. And the last question from many, many bosses, But can we solve the problem by software? This is many times you know that this is impossible. Okay, so this is the general picture about failing EMC. So what can you do? This is not easy. This is from any book in EMC. This is theory. We know theory, but sometimes we don't apply or we cannot apply this theory. When we have a prototype, we test, I don't know, voltages, currents, efficiency, temperatures. How is the firmware working? So why not do a review of EMC topics, EMI topics? This is the idea. So you need to prepare your own checklist. There is no any specific checklist for everybody. You need to prepare to build, starting from some list from other people. You need to modify this list that match your needs, okay? And additionally, remember, not because you have an EMC department, an EMC expert, that means you are doing EMC review. Many companies with EMC people have the EMC people working in solving problems, not reviewing the new designs that will go to production. So what can you do? Of course, this is not a full list because we don't have time, but let's review things that obviously you know. For example, remember to review emissions and immunity, both of them, not only emissions. Another idea, add experience to your design. Don't permit that the experience for your people is lost. Add the experience to the checklist. Another important idea, find the limits or the legal regulation you need to pass, where you are going to sell the product in the next months or years. What kind of requirements about the environment, no? Industrial, residential, blah, blah, blah. No? In this way, for example, if you know that this is the limit that you need to pass, you can think about, for example, why we are switching at that frequency or we are not switching at this frequency. No? If you can switch in the area where the limit is less restrictive, you will have less problems in EMC. But to know this, you need to check, to study, to analyze the regulations of your product. Another important idea is consider different elements. People usually, when doing EMC review, check, of course, the schematic, sometimes the components, and of course, the PCB review. But this is not usual to review the mechanical design or the cables, especially the mechanical design. In the past, I don't know, 3-4 years, I have been teaching courses in big companies only for the mechanical people. It's people that has no knowledge about electronics, but they are very important in the EMC behavior of the product. We will talk about this later. So don't forget EMC mechanical design in your review. So let's start. Let's go to the components. For example, if you are reviewing your design, you can check how is the technology you are using. Is through hole, is SMD components. You know, SMD components means less parasitics. That is because radio frequency people is working with as small components as possible. Okay, so think about that. Another important thing, for example, is the idea of modeling your components. This is the response of one PFC inductor, where you are expecting from a PFC inductor or from any inductor is something like this. This is the impedance, no? Omega L. But in big inductors, sometimes you have not only one, you have several resonances. And these resonances are related with the profile of emissions of your product. So you need to test the components with your impedance analyzer, up to 30 megahertz, up to 100 megahertz. It depends on your application. For example, you can think about spread spectrum techniques. Oh, we are going to use this clock, but let's select the spread spectrum version of the component. Or perhaps you can use, I don't know, low EMI versions. In MPS, for example, you have drivers, or you have circuits for power for DC-DC converters with the possibility to configure a low EMI version. What is a low EMI version typically? Perhaps they are using some spectrum techniques, but usually the most important thing is the rise and fall times. Is the DVDT and the DIDT. in any company, it's very important. Someone saying like, can we work slower? Why we are working so fast? Is really needed to switch so fast? Okay, you know, gallium arsenide or silicon carbide, we are worried about efficiency. We need to switch very fast. So that means very good news for EMC consultants. Okay, obviously, sometimes it's impossible. But if you are designing a product that don't need to switch in 1 nanosecond, why to switch in 1 nanosecond? Why not to switch in 100 microseconds if the product is not a high-speed product? Okay, this is related with the drivers in the technologies you are using, no? Or perhaps the manufacturer of the microcontroller in some point change the drivers, and suddenly, from the EMC perspective, your product is creating more emissions. And you say this, the typical answer, the typical sentence is, there is no changes. It's the same product. No, it's not the same product. This component has been changed. Now it's switching in this way, and in the previous model, they are switching in this way. So you have more energy in high frequencies. You can see this here, no? You see the typical digital or square wave signal in electronics. If you increase the rise and the fall time, it's not so nice for digital people, no? Digital people want 0 and 1, 0 and 1, 0 and 1. But remember the sentence, marvelous things happens between the 0 and the 1. In EMI and in EMC, the important thing is the IDT and DVT. Okay, you can see here how is the difference in the bandwidth of the signal. If you are switching in 3 to 2 nanoseconds, the bandwidth is around 100 megahertz. If you switch in 10, 15 nanoseconds, the bandwidth goes to 30 megahertz. That means less problems with cables, with the slots, with PCB traces, things like that. So this is a very important part of the review, is what kind of components, what kind of technologies are using. Perhaps we can change this to other slower technology. A schematic review. This is related with taking the sheet and considering things like, for example, this. This is in the first position. This is not especially for EMI, but in my opinion, it's very important. Have you test points? I have been trying to solve problems in very complex circuits where there is no test point for the main signals. So it's impossible to do debugging. You have long pigtails to connect the probes to the ground system or things like that. So you need to think, this signal is of interest for me while debugging, okay? Or for example, you can think about ground symbols. This is very important to design the ground system. Is using different grounds for power, for analog, for digital, how they are connected. Single point series, single pole parallel, star. It's a multiple structure. You need to review the ground system. Very important for EMI. Have you introducing protection in the, or filtering in the input output pins? The signals that goes to connectors, very important. Why? Because these signals goes to cables. And cables are the most important antennas in your product for immunity and for emissions. Another important topic, decoupling. Check that all integrated circuits, all the important circuits like switching devices, drivers, power amplifiers, in audio or in high-speed digital circuits, have some kind of bypass or decoupling capacitor. How many capacitors? What technologies? What values for these capacitors? Different values, the same value, microfarads, nanofarads. This is very important. We will talk about this in tomorrow in one speak about power integrity and EMI. Very, very important. And finally, and not less important, if you have instructions for the layout designers. Many companies are sending the design to external companies doing the PCB layout. So you need a very, very good communication. If not, the design in the PCB will not be what you want in the schematic. You need to introduce comments. And of course, you need to specify things like, for example, shielded areas or isolated areas. This is part of the review from the EMC point of view, not from the functional point of view. The PCB. The PCB is one of the most important, if not the most important thing in EMI failures. The PCB is the way you connect things in a small board, no? In different sizes, but you are printing the connection in some way. No? In 40, 50 years ago, this was transparent, was not important. Auto router was very easy to apply for any design. Today it's more difficult to do this, no? So what can you check in your checklist? The most important thing, in my opinion. No, perhaps the most important, yes, the most important. There is another important thing we will talk this about. PCB stack up. How many layers? Of course, in very sensitive products, considering cost, like home appliances, automotive, or lighting, things like that, the answer is we are going to use 1 or 2 layers. Be careful. 1 or 2 layers are very, very dangerous in EMI if you have a medium complexity circuit. Very, very difficult to implement good EMI practice, no? So you don't need to compare 2 layers cost with 4 layers cost. You need to compare 2 layers plus filters, ferrites, and components to solve EMI with 4 layers cost. This is the real comparison. Right? In my experience, when we have switched from 2 layers to 4 layers in radiated emissions, the difference can be 30 to 40 dBs less, only changing to 4 layers. Obviously, you have more layers, you need to think more in the review, no? You need to apply things like this, no? This is a typical solution that many people is using when designing a 4 layers board or multi-layer board, something like this. Let me use this one. Okay. Here, they dedicate 2 layers for signals, 1 layer for power, 5, 3 volts, I don't know, the different voltages, and 1 layer for ground. This is not good. The good structure could be something like this. Remember that nothing is good or bad. In AMI, the best answer for any question is it depends. Nothing is the best option, no? In this way, you will not have mistakes. So remember, you have 4 layers. It's more important to have 2 ground planes and to use white traces for the BCC lines for 3 volts or 1 volt than using a full plane for BCC, for power. The second thing to consider in the PCB is the partitioning, where you put things. You need to consider that you have a DC-DC converter. Jan is expert in EMC with DC-DC converters. So DC-DC converters are very noisy if you don't take care about that. You cannot put the DC-DC converter close to connectors because you inject noise in the cables. You cannot put DC-DC converter close to sensitive areas because you will introduce noise, no? This is the idea of partitioning. You can compare this with a city, no? You have a product, what is the power electronics area, or what is the, I don't know, the radio frequency area? It's something like this. It's something like, for example, the industrial area or dump. And what is sensitive in your circuit? In your circuit, sensitive is something like the hospitals and the schools, no? It's your small. So if you are trying to consider where you put the connectors that the trucks are using to go to the industrial area, you try to put the traces, the streets for these trucks far from the schools or from the hospitals to avoid problems, noise, or things like that. No? So this is the idea of thinking in partitioning. In the mechanical review, we will do the same with the product. Is where you put the filter, where you put the amplifier, where you put the power supply. It's very important to think about this, and it's part of the mechanical design too. Another important thing to consider is related with component location, where you put, for example, inductors. Inductors are very, very aggressive, and they are very, very sensitive. So you have 2 PC boards, and you put one on top of the other. And in one of the PC board, you have an inductor, for example, for filtering. The noise that is coming from some aggressive area will be introduced in the inductor and will go out, so you will fail in conducted emissions. So these kind of things must be reviewed. No, no, no. You are connecting, you are locating this inductor in the wrong position. Or instead in this position, rotate 90 degrees. So he will be less sensitive to the noise. I don't know, these kind of things necessary for to have more success. Have you the possibility to have this, the sensing? What is the sensing? The sensing happens when you have a wireless device in your product. Wireless communication like CB, Bluetooth, Wi-Fi. If you put these elements close to aggressive elements, like for example, DC-DC converters, you will have a lot of noise and the receiver will not be able to work with a good signal to noise ratio. And you will fail in communication or you will have less coverage, no? So be careful about the sensing. In this picture, I am trying to explain that if you have the origin of the noise in this area, the noise is being propagated to other area that fails. This is the idea. Because the energy don't goes through inside of the conductors. The energy goes inside of the traces. The energy in our circuit is around the conductors. They are electric and magnetic fields that are carried around these traces and these cables. So you don't have a good control of the energy is spread around and arrive to the non-good areas. Let's say another important thing to review. Another important thing to review is the layout. For example, are you using very long traces? These very long traces are aggressive and sensitive, so you can create crosstalk problems. You have critical signals in the edge of the PC board. This is very dangerous. To have critical signals, aggressive or sensitive, in the edge of the PC board, create the possibility through the fringing effect to have radiation or pickup from the environment. Very important to review these critical signals. Or for example, you need to consider you have some signal integrity issues, no? If you have a very high speed signal, you need to consider you need to introduce in your design a uniform transmission line. That means microstrip, strip line, and this line must be terminated. Remember, you have signal integrity problems, you will have EMI problems because you will create common mode voltages, and these common mode voltages excite the cables. Okay. What about the layout of protectors or filters? You need to apply radio frequency techniques. You need to put short and wide traces, good connections to ground or things like that. If not, the protector will not work as intended. This is part of the layout review. The second most important part, remember my first comment was related with the stack up. This is the second one, is you need to avoid slots in ground plane. The ground plane must be continuous. And if you have some kind of slots, never a trace must go on top of the ground of the slot. If you have some kind of signal going on top of the slot, what happens is that the return currents take this path, something like this. And what is this for the current? This is impedance. So you have current and you have impedance in this part. You have what? You have voltage. So between this point and this point, you have a voltage. And this voltage will be exciting the cables. And then the cables will be like monopoles or dipoles. You will radiate. This is sometimes intended if you separate the analog and the digital grounds. So my advice is, if you don't know what you are doing, don't separate analog and digital grounds. Full ground plane. If you are separating, you know what you are doing, because this effect, I want to avoid this effect. But in general, the idea of separating is not a good idea if you can put aggressive and sensitive areas far from one from the other. So you will not have common impedance problem. That is the problem you want to avoid, creating different grounds, okay? More things to consider. Decoupling. In the schematic, I saw that we are using 2 capacitors, but how the capacitors are located in the circuit? Are close to the device with a good layout, minimum traces, with white conductors, with a good connection to the ground planes, with vias. How many vias? 1, 2, 3. Okay, this is something that can be very useful, especially for high frequencies. Or if you need to shield specific sensitive areas or aggressive areas. No, for example, you have amplifiers that have a high gain, very high gain. They are usually very sensitive to electric fields because they are high impedance circuits. So they pick up electric field lines and they amplify the signals. These areas perhaps can be shielded in the PCB, and the review was not done. Mechanical design. We are good in time? How much we have now? 15 minutes we have. Okay, perfect. Mechanical design. This is very important. And here is where your people, your mechanical people need to be trained in EMI, or at least to be working with some electronic engineer with EMC knowledge. One of the things that is very important in mechanical design is that any mechanical enclosure has resonances. That means that some specific frequencies related with dimensions, you have magic. You can test this before you have the prototype. You apply simulation. For example, we are using HFSS from ANSYS, but you have CST, you have EM Pro from TSI. You have a lot of different software in the market, no? But the idea is that with this simulation, you can understand at what frequencies your product is sensitive. So if you identify that you have a specific resonances, and this is a general idea, not to explain in detail. For example, you can see that this area is more quiet than this area. So it's not a good idea to put a sensitive element close to the hot area if in your circuit you have these kind of frequencies inside of the circuit, because the energy can go to this area more than to the quiet area. Another important thing about shielding is not the material. The material is not usually important. Material, aluminum, steel, copper, I don't know. The different materials used for shielding are not important because you can obtain more than 100 dBs usually with any metallic material. You will select the material because of the cost, the aesthetic questions or something like that, no? There is only one exception, is if you have very low frequency magnetic field. You have very low frequency magnetic field, that means DC magnetic field, 50, 60 hertz magnetic field, 100 hertz, frequencies lower than 1 kilohertz, and magnetic field, not electric field, then usually you will have problem shielding because this energy is able to go through metal very easily, okay? So you will need to make other solution like rotating the element, or you can introduce some kind of high permeability material like new metal, nickel, I don't know, depending on your product, no? But in general, the material is not important. What is really critical is this, is how are the slots in your design. If you have a slots or apertures like this one, you have the probability to radiate or to pick up energy. Okay? A general rule is that if you have a signal, let me write here, if we have a signal at some specific frequency, the size of the signal is 300 over the frequency in megahertz. So for example, if your maximum frequency is 300 megahertz, look at this, wavelength is 1 meter. So a 300 megahertz signal is in this size. So when you have problems with this signal in your circuits, in your PCBs, in your cables, in your slots, when the size of the slot of the cable of the trace is in the order of magnitude or bigger than lambda. So you want to be happy, you will try to put what? Dimensions less than lambda. And a typical rule for commercial products is that dimensions be less than lambda over 20. Okay? You want more confidence, you can go to lambda over 100. That means less and less and less in size. No? For example, for 300 megahertz, lambda is 1 meter, 100 centimeters. So lambda over 20 is 5 centimeters. So if easy review, is to go to the mechanical design and to check that there is no slots or apertures longer than 5 centimeters. Remember that sometimes you looks like the metal is making contact, but you have non-metallic paints, you have some kind of surface treatment that is non-conductive, no? Anodized aluminum or things like that, that you have the slot. So in this area, perhaps you need to connect some kind of fixed screws, or you can introduce some gasket. I don't know. There is a lot of possibilities, but this is the first thing to consider. The slots and apertures, ventilations. The other possibility to review is the input and output of cables. You have the perfect silt, but you open a hole, and through the hole you put the power supply cables, the USB cables, the Ethernet cables, I don't know. Then the energy go in and out very easily. So usually it's very important to filter or connect properly the silt of the cables in the enclosure. You can test another, you can check another things in your mechanical review. For example, where the filter is located, no? Remember that filters must be always exactly where the cables go in and out of the product, not far from the input of input cables. Because in this situation, you have noise from your product, this noise goes to the cable and go out. But if you have energy externally, something like this, you will pick up noise with the cable and the energy will go inside before being filtered. So the filter always must be close to the input output of the cables, okay? So it's part of the mechanical design. When you are designing the mechanical structure, you say cables go in this position, so this area is for the filter. And better if the filter is shielded. This is magical, okay? You need to check things like this, not only in cables, you can check in the PCB. Never input and output of filters must go one close to the other. You will create feedback, check that. Floating headsinks, especially in power electronics, if they are big headsinks and they are floating, you will have a strong metallic element doing a DVDT. So you have a lot of electric field inside of your product. Perhaps you can connect the heatsink to ground, perhaps not possible because of safety, and you need to connect with capacitors, or you need to separate from chassis, I don't know. But you need to be careful about this kind of headsinks. They can radiate, if in big size, something like this, they can radiate, I don't know, 600 megahertz easily, okay? And review if in the mechanical design, some cables can go close to the slots or apertures. You have more probability to excite the apertures, and the apertures will be radiating, no? So usually I check that the distance between the cables and the slots is at least something like 1 centimeter. Remember, cables must be close to the chassis, always. This is a good option. All cables must go close to the chassis, not through the air, with some distance to the chassis. So you have common mode currents, you are not creating a loop. But there is one exception. If in the chassis, you have a shield, a slot, a seam, or something like that. Because if you put the cable carrying high frequency energy close to the slot, you will excite the slot, and he will be working like an antenna in emissions and immunity. Cables, what you need to consider in cables? 2 minutes to finish. You need to consider that cables are the most aggressive antennas in the range from 30 megahertz to 400 megahertz. So how is the best number of cables for your product? The optimum number, 0. Remove all your cables. This is impossible. So minimize the length of your cables. Consider if you need transmission lines, uniform transmission lines, twisted pair, coax cables, or things like that. And additionally, you can look for non-very good retro paths. For example, in a flat cable, you can put the clock signal in this line and the ground signal in this conductor. So you are creating a big loop. This is something that is easy to review, no? It's better to put the clock wire, and close to the clock wire, the next one is a ground wire. No? It's very easy to do. Remember that ground grounding the shield of the cable must be done to the enclosure, not to the ground of the PCB. Must be done exactly in the chassis and exactly in the point where the shield is going into your product. So this is the good position. And basically with 360 degrees around the perimeter of the connector, okay? You are using a plastic connector, this is impossible, no? So it depends on the product you are working with. And you need to avoid pigtails, okay? You need to consider to minimize the inductance of this element. Don't forget firmware. You can do a lot of things. In immunity, watchdogs or different techniques to have a more robust product. And in emissions, you need to do something like, for example, apply spread spectrum techniques. In power electronics, this is very useful. Or you can stop some area that is not working specifically in some part of the time. I don't know, a lot of things to do with firmware. And test circuits. You will see in the demos, I will do later that with instrumentation, you can do a lot of things with your prototypes. This is the product we will be testing today and tomorrow with the demos. So thank you. We are on time, I think. So if you have any question, I will be happy.
So here's the moderator, Julia Meyer again. We are first taking questions now from our on-site participants.
Suggesting for some test points and some signals. Could you please a little bit clarify on high frequency signals? Would you still suggest?
Yes, the question is when we are talking about test points, what kind of test point with an example or something like that? Consider, for example, you are working in power electronics. You have a device that is switching and you want to see if the switching activity is creating ringing. It's very difficult to see if you have a high frequency ringing in hundreds of megahertz, if there is no a good possibility to put the probe, the voltage probe, no? You will need to make changes that are very difficult, no? So this is one typical thing you can want to test, or a clock signal or things like that, no? High speed signal. More questions? You don't have problems in EMC? No. No problems? No questions?
So Arturo, there are some questions from the online audience. So the first one is, could you repeat the name of software to simulate problems with enclosure?
The software I was using here is HFSS from ANSYS.
Okay, thanks a lot.
You have a lot of other options in the market, of course. This is the one I have.
So the next question would be, why is it often better to have two GND layers versus one GND and one of VCC layer if the GND and VCC layers are very close to each other? Very low impedance.
I think I understand the question. This is a very complex topic, but considering this plot, the idea is that you are using a plane for the VCC line for, consider, for example, 3 volts. For the signals in layer 4, the layer that is S2, these signals will find the retro path in the power supply plane. So you will have a lot of noise in this power supply from the signals in layer 4. So this is very dangerous. The advantages of connecting VCC and GND in a normal PCB are not very big because the distance between them is not very small. The only advantage for connecting VCC and ground planes, one close to the, is to put one very close to the other. Okay, if they are not very close, you will not have that kind of decoupling effect through the full PCB. So in general, it's better this. So you have the possibility to have for different signals a good retro path between them. Okay, close to the signal. Okay? This is the idea.
Thanks a lot, Arturo. So the next one is, you do not suggest to use shielding. Am I correct?
No, I suggest to use shielding if necessary. If you have a sensitive area or a very aggressive area, shielding this specific area in the PCB can make a lot of advantages later. No, if not, the people in the design of the mechanical enclosure will need to shield the full product, and usually this is more difficult. No, you can use shield.
So we take 2 further questions and then we will switch to the next session. So please stay online here in the webinar. So the next question is, what is the best way to design and connect 2 different power planes on a multi-layer design PCB? As an area or as a point connection?
2 different ground planes.
Power planes.
Power planes connected. Oh, sorry, I cannot answer that question. It's very broad. There is a lot of possibilities to answer the question. I would need to know more about the problem. Sorry.
Yeah. So the guy who asked the question, we will come back to you via email.
Yes,
and,
of course.
And so we take one last question. How would you protect sensitive tracks in a power converter, like feedback lines, against EMC pickup from the high noise nodes, like the power tracks switch nodes?
Oh, if you, this is the easier answer for this is you can look for the data sheets of converters like MPS, and you will have a lot of information about how to put this element. No, usually is to separate from the switching node, to make the switching node as small as possible, and to perhaps to put this, if possible, in a different side of the PCB. No, so there is different techniques you can apply. Okay.
Thanks a lot, Arturo. So we have a lot of more questions, but as I mentioned before, we will come back via email to you. Now we are changing the setup, so please stay online here. We will hand over in a few minutes to Christian Reimer, who is specialist for EMC systems and solutions at Rohde & Schwarz, and he will present about EMC testing from first level debug